Hello everyone, today we'll be going over a system design course today, and today we're working with graph-like data models. Now, to be able to go over the concept of graph-like data models, it really focuses on the shift from tree-structured document models to graph-like data models, which are driven by the need to represent complex many-to-many relationships naturally. In graph-based models, the world is interpreted through two fundamental elements: vertices and edges, where the vertices represents entities and the edges represent relationships. So when combining both of them together, we already see that the vertices are the objects of interest, while the edges are akin to the relationships that bridge the vertices together, creating a web of interconnectedness. The interconnectivity is not just a theoretical concept, it's prevalent in numerous real-world scenarios. So let's consider social networks, for instance, where we have individuals, which are the vertices, form friendships or acquaintances, edges, with each other. There's the boundless realm of the internet, for instance, with web pages as vertices connected by hyperlinks. So I want to point it out for the internet as an example. We have web pages and hyperlinks, which are considered the vertices, and the hyperlinks as edges. And this is not also applied for the internet, but this is also applied for transportation networks, such as junctions, airports, or stations, and the vertices representing roads, which could also represent the routes for them to be able to get from point A to B. Overall, graph models excel where entities have diverse and dynamic relationships. So they excel with diverse and dynamic relationships. Let's move this out of the way. Let me just respell this. And overall, they provide a universal framework capable of encompassing various types of vertices and edges within a single unified database. Capable of putting relationships in a single unified database. Which overall streamlines the complex data integrations. This adaptability is why platforms such as Facebook leverage graph databases to integrate different types of user activities and relationships seamlessly. And we have an example.
One of the most complicated computations that we do on the site is the computation to tell how you're connected to people, right? Because, I mean, if you can imagine that's stored as sort of a series of I guess, undirected, it's not weighted, so undirected, unweighted pairs of ID numbers of people in the database. Then if you want to figure out who's friends with someone, you have to look at all their friends, right? So that's maybe like 100 or 200 people. But then if you want to figure out like who's a friend of a friend or what the closest connection is there, then you kind of have to look at the 100 or 200 friends of each of those friends. So it becomes like at each level, there's another factor of n multiplied in, where n is the number of friends that each of your friends has. So you can see that this kind of becomes exponentially difficult to solve for the shortest path between people. So I mean, if you're just looking for a friend of a friend, that's n squared. If you're looking for a friend of a friend of a friend, that's n cubed. And I mean, that's something that traditionally was pretty difficult for a lot of the predecessor sites to Facebook. So, and for example, Friendster had large problems with this because they were trying to compute paths 6 degrees out or like 7 degrees out. And I mean, that's something that when you're doing like n7th, like that just is really I guess, very hard, and took down their site for a while. So, one of the things that we kind of had in mind when we were figuring out how to do this was, how do you distribute the database in such a way that this computation becomes manageable? So what we decided was that everyone on the site does most of their activity at the school that they're kind of based at. So if you're at Harvard, then like most of the people who you're going to be seeing or transacting with on the site are going to be at Harvard. It's actually probably like 90% of the stuff that you do on the site. So we decided to split up the databases and create one instance of a MySQL database for each school on the network. And
so overall, that is just a vivid example to be able to showcase graph-like data models overall. And every data system that we have is going back from most of our lectures. Every data system is going to have a database, cache, and queue to be able to have a data-intensive system altogether. Overall, employing graph databases has quite a set of unique perks, actually. So graph-like databases, let me just move out of here for a second. So the perks, for the most part, really come in handy. So other examples could also be PageRank when you ever search on Google or Bing or whatever platform you use. So search engines. And then they can also navigate web pages based on popularity. There's also travel routes on a map. Whenever you're trying to get from point A to B destination, depending on what you're trying to filter. So there's filtering. Just to give a few examples over there. Just going to highlight that. But beyond these following examples, graph models offer something more. They offer a more natural and flexible approach to data evolution. As applications continue to grow and requirements shift, the graph model can be extended without uprooting its core structure, making it resilient overall for a long-term data management solution. So it's great for a long-term data solution. Just zoom out of here. There we go. Let's head over to our concept example to further cement this. Now, in our concept example, let's imagine mapping out a family tree or visualizing a circle of friends online. So overall, each person is a vertex. We have, for every single graph model, we got to know what are the vertices and what are the edges. In a family tree, the entities are going to be the family members. And overall, the relationships are considered the edges. Like, just how are they related? So overall, if we were to have a family member, we would, for instance, have mom, dad, brother, sister, all connected in a graph one way or another, such as mom, dad, they're connected union. You have brother, sister in one case, and that's considered a family. Just an example overall. So you can have a directed or undirected graph, weighted, depending on the context of what you are going for. But overall, if we were to, for instance, picture two individuals, let's take a further in-depth example. Two individuals. In fact, I'll just put it was made over here. Sorry. Okay, excuse me. So now we're picturing two individuals. Let's call this person Lucy from Idaho. And then Alan from New France. Despite their diverse origins, one being American, one being French, they share a life story together in London, a bond depicted as an edge in our graph. So we have Lucy over here, then we have Alan, all connected by a relationship that they have, that they were in London together at one point. So if we were to apply this in a graph database, so every data system is always going to require a database, cache, and queue. That's always a data system whenever you're deploying something. So if we were to put in a graph database, examples which come into mind that one could employ, deploying in the database, a graph model would be Neo4j, which would encapsulate the relationship, residence, and origin, so as parameters. Overall, respecting the varying granular, overall just respecting the different modes of diversity within the data that we have. We will also consider state and city as well, if need be, just adding parameters within it. Overall, this flexibility of the graph model allows us to be able to differentiate the structure, and we could have different regions in particular. So like the United States has a state and city, and France would have boroughs in particular, depending on where. And the graph model has the flexibility to be able to actually adjust between different parameters and such. So we adjust between different parameters. One second. It allows us to have a versatility based on the graph model. In a traditional database, such rich and intricate relationships might become convoluted, buried under a pile of join tables and foreign keys. It would just take a very long time to be able to actually find the relationships and be able to add on new parameters. So if we were to picture a database, namely, we can imagine it as like a MySQL database, as Mark Zuckerberg was also mentioning about it. It was very hard to be able to do and utilize, but the graph-like data model, or any database that relies on graph modeling, allows us to be able to make intricate connections and be able to add on more parameters that we could actually find and can join those relationships together. Excuse me for a second. So overall, as the application continues to grow, it allows us to add more flexibility depending on the intricacies of the following data that we need to be able to integrate new vertices and edges as the data universally expands. So if we're adding on more type of vertices and relationships, like for instance, Lucy's family wants to meet Alan's family. So we already have, we can have a series of one family over here, Alan and their family, and they're connected one way or another, in either an undirected or directed graph, depending on the context of the data. So let me just move out of here. There we go. And feel free to take a screenshot. Now, for us to be able to solidify our concept, let's go over a practice problem for graph data-like models. So in the context of social media and a social media platform, the graph data model is key to mapping the intricate web of user interactions, connections, and content flow. So for graph data model, we focus on user interactions, connections, and content flow. Utilizing a graph database, so mind you, whenever we always have a data system, we always need a database, a cache and queue, So an example of a database that we could use would be something like Neo4j, which allows for a modeling of users, their posts, likes, and comments. So users, posts, likes, and comments. And follows as vertices with relationships between them as edges, so they will all have relationships. And whenever we have relationships, we always need to remind ourselves that graph data models always have vertices and edges. And we know that the edges pertain to the relationships of all the post, likes, and comments, for instance, and the vertices can also mean specifically the post's likes and comments, and also users as well. So we already have that in this context over here. So this setup enables a nuanced understanding of user engagement, content variety, and community formation. A distributed cache would leverage graph queries by messages and further posts and further comments as well to be able to update the current user interface and can provide instantaneous access to feed updates and notifications. So we would have a distributed cache for updated access. And the queue represents the user's actions. When interacting with the platform. So when interacting with the platform. So for step 2, So then the next step that we would need to understand is create a workflow diagram And the workflow diagram would be as follows. When a user posts new content, the system employs a graph traversal. So when user is posting new content, the content is considered the vertices, and the relationship of that content is considered the edges. So we would also know about the network and fan out method. Remember our Twitter example and our fan out methodology. Which would be the edges. So overall, we will understand between analyzing the edges for connecting the strength and in recent interaction of history. The platform will utilize content delivery by managing the most engaged followers and optimizing maximum engagement. There are updates to the graph database reflecting the interactions and overall enriching with data on content popularity and engagement patterns. So, and then the next part that we would need to consider after we set up our whole database system that we've already set up in place is that we need to always consider faults and failures between the hardware, software, and human side. consider all faults and all potential faults which could lead to failures. So we need to ensure that the platform's reliability involves safeguarding the integrity of graph data, crucial for maintaining user trust and engagement, and strategies to deploy redundant graph database nodes. So we need to deploy redundant graph-based, well, technically graph-based vertices and also handle traffic volume for reliability and scalability. And quick recovery from errors. From the hardware, software, and human side all together. These following measures ensure that the social media platform is resilient even under stress of viral content and rapidly evolving user networks. So let me just zoom out of here to give you a deeper understanding. There we go. And let's move over to our second practice problem. Feel free to take a screenshot as well. And now let's go over our second practice problem. So in our second practice problem, we're focusing on a map for restaurants using a graph data model. So the number of steps that we have to do, and I'm just going to go straight in the steps for this. So the first step that we got to do is understand, let me clean that up and use a different color. The first step that we got to do is understand the connected components within the graph data model. So understand the connected components with a graph data model. And as we know, from every data intensive system, every single one's going to have a database, cache, and queue. That's right. Every single data system is going to have that. It's essential. It is needed. If you don't have it, you don't have a data system. Isn't it obvious? Anyway, for a map-centric restaurant discovery service, a graph data model illuminates the relationships between users, restaurants, reviews, and location data. And for every graph model, we always know that there are two types of parts that make up a graph model. We know that there have to be vertices and edges. Edges always signal relationships, and vertices represent entities. Edges, relationships. So for restaurants and a map, we have users, restaurants, obviously. I'm going to use a different color for this. We have restaurants, users, reviews. We can go off on this forever. Use and locations, because we also have miles as more meters, kilometers, depending on which distance really. And the relationships are always the edges. So the edges for the most part could be the relationship of the, it could be overall of the distance, the type of menu, all having different forms of connectivity as well. So locations, we put it as vertices, but then we already put in for the distances between them. The type of menus relative to the restaurants as well. Maybe they're grouped all together, or maybe there is just something that's connecting them. Maybe it's a franchise as well. So maybe you're looking at different franchises. Again, we can go off on between vertices and edges for the graph data model. So in terms of a robust database, a good example would be of a Rango DB, Rango database. where it facilitates advanced features like personalized recommendations, in efficient route planning for restaurant visits, and dynamic update for restaurant popularity based on user interactions. The distributed cache we would need for consistent updates and real-time access to restaurant ratings. So we can put in ratings, for instance. And the messaging queue will be bookings, for instance, timely updates for information and reviews. So this can also be messaging queue for reviews. And overall, this would be just the first component we need for a graph data model. So now the second step that we need to do is drafting a workflow for our graph data model. And the way we do that is that we need to consider the user searches for restaurants and how the user is going to be interacting. So we got to ask ourselves, how will the user interact? Between our whole data system. Between and within our whole data system. And we do so by understanding the social connections between location, preferences, and reviews. So we can do location, preferences for taste, and reviews. That's a filtration criteria that we actually understand between the whole graph network. And there will be consistent updates to capture new reviews and visits, and there's dynamic adjustment with restaurant rankings and visibility on the map. So there's also dynamic flexibility and adjustments. For restaurant. Ratings and reviews. With visibility on the map. Map data models are great for filtration. Graph. Yeah, graph data models are great for filtration. And finally, that we have to do for every data system that we already built out, we always need to consider the faults that may lead to potential failures. Consider all faults and potential failures. And we do so to maintain the service's efficiency and accuracy. We always need to look at the hardware, software, and human side. Prone to errors. And we overall need to figure out and understand more, aside from efficiency and accuracy. We need to manage the graph's data models, integrity, and reliability. So we always need to consider the integrity, reliability, and scalability. Okay. And this overall involves implementing redundant storage. To be able to not only keep track of the user's logs and interactions within the data system for changes, but also if there are more restaurants being added, and also protecting current data if it's lost. The following precautions would also ensure that the restaurant discovery service maintains a trusted and open, up-to-date resource for users to navigate within their current preferences. So let me just zoom out and clean this up for you folks so you all get a deeper understanding between it. Let me just move 3 over here. There we go. Okay, and move this right here. And so yes, this was graph-like data models within our system design course. And thanks again for taking time to watch this. If you found this helpful, be sure and feel free to like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And by all means, if you want to be able to refresh any concepts that you need to, or feel free to pause and take screenshots along the way, by all means do so. And as always, take care. Cheers. Bye-bye.